Is Dr. Toyoki Kozai.
Okay. Thank you. I'd like to thank the organizing committee for giving me an opportunity to talk about the role of plant factory with artificial lighting in vertical farming. My topic today, after introduction, I will explain the concept of Cpps, or closed plant production system, and its application as a plant factory with artificial light, or PFAL. Then I will describe about the concept of resource use efficiency, RUE, and explain resource-saving characteristics of Cpps. Then I will show the method of online estimation of resource use efficiency and rate variables, such as the net photosynthetic rate. Then talk about integrative environment control system and ubiquitous and in-town PFAL. And finally, challenges in vertical farming. Center for Environment, Health, and Field Sciences of Chiba University, where I work for, was established in 2004 with missions to develop sustainability science with special science, a special reference to food, health, and environment, and to develop urban horticulture science and technology to contribute to society. And people-oriented, people-centered civic science and contribution to sustainable town management and planning. And production of horticulture, medicinal, and amenity plants under controlled environment, and the interaction between plants and people. And when our center was established, there was no building around our center, except for the new railway and the railway station under construction. But 7 years later, last year, there were several tall buildings. And this is the corner of our research center. And there is a plant factory here, and my office here, and the bee culture garden here. And my home is here. And there is a rooftop farm on the shopping center, and my organic farm garden is located here. And there is an organic restaurant here where they serve vegetables grown here. And there's a hospital serving the Oriental medicine. So you can call this a future vertical farming city. And our plant factory project area of Chiba University is like this. There are 2 plant factories with artificial light here and a greenhouse complex with floor area of about 1.3 hectares. One PFAL is for growing crisp head lettuce in this way. Another one is looks like this, operated by Mirai Company Limited. This is inside view, producing about 3,000 heads per day, or 1 million heads per year. And they are selling this. The annual productivity of leaf greens per unit land area is over 100-fold compared with that of field-grown leafy greens, because there are 10 tiers or 10 layers, and decrease in culture period by half through optimal environment control, and the number of days per year usable for culture is doubled by year-round production, and planting density can be doubled, and production value increases 1.5 times because of improved yield rate and high quality resulting from no pest damage and weather disasters. So 10 times 2 times 2 times 2 times 1.5, 120. And this is a photograph of leaf lettuce plants grown in PFAL on sale at the supermarket. On plastic bag, it said no pesticide used, clean enough to eat it as fresh salad without washing. But most leaf vegetables are sold to a chain restaurant because they buy at a higher price. Plants suitable for plant production in PFAL are those which grow fast at a relatively low light intensity of 200 micromole or so, and at high planting density, and almost all part of plant is edible or saleable at high price. The electricity cost per saleable plant weight become low. So examples are transplants or seedlings of all kinds, and leafy vegetables, herbs, root crops, small root crops, and herbaceous medicinal and aromatic plants, and short height plant with high added value or functional plants, such as Japanese horseradish or miniature rose, miniature orchids or bedding plants. Generally, plants for staple food to intake calories, such as rice, wheat, potatoes, etc., are not suitable or economical for production in PFAL. Now, I would like to define some of these terms: CPPS and PFAL and RUE. CPPS is schematically shown in this diagram. Yet almost all resource inputs are converted into high quality produce. Then resource consumption is minimized and no environmental pollutants are emitted to the outside, resulting in maximum resource use efficiencies and minimum cost. This is the kind of concept, but to realize this concept as possible as we can construct this kind of system. The components of CPPS are air conditioned with fans and thermally insulated, almost airtight walls, and lamps for giving light for photosynthesis, and the CO2 supply unit, and nutrient solution supply unit containing inorganic fertilizer. There is a multi-tiers with light source here. But large amount of electric energy is needed to operate air conditioners and lamps or pumps. This is a photograph of a CPPS with total floor area of 500 square meters, developed in the year 2000 at Chiba University. 7 tiers and automatic plug tray transportation system and automatic precision irrigation system are installed. All units are controlled by distributed intelligent control system. But it was too expensive to be commercialized, So we developed this basic unit of CPPS with a floor area of 16 square meters for production of mainly transplants. And this was developed in the year 2004 and commercialized in 2005. And currently, about 280 units of CPPS of this type are in use at more than 120 locations in Japan this year, just for transplant production. There are two rows and 4 layers, holding 96 product trays. This is another CPPS consisting of 4 basic units holding 384 product trays, and the production capacity is 250,000 plants per month, or 3 million plants per year. This is the largest CPPS in Japan, consisting of 21 basic units with a total floor area of 476, with a production capacity of over 10 million plants per year. And in Japan, most PFAL was constructed with the concept of CPPS because it can realize concurrently highest yield, high quality, and high value creation as scheduled all the year round, and highest resource use efficiency, bringing about the minimum resource consumption and minimum emission of pollutants at lowest cost, and provide comfort working environment for humans, and provide profit-making business, job opportunities, and high quality of life. So this is a bit difficult to understand, but this is the definition of resource use efficiency. Resource use efficiency is defined as amount of resource fixed divided by amount of resource fixed or field in produce divided by amount of resource input. Essential resource for growing plants are water, CO2, light, and ionic fertilizer. So we can define water use efficiency as amount of water held in plants divided by amount of irrigated water. The same as CO2 use efficiency and light energy use efficiency and fertilizer use efficiency and electric energy use efficiency. This is an example of experimental data of water use efficiency. Here, 2,100 kilograms of water was supplied for irrigation, and they are absorbed by substrate and plant and transpired to the room air. Then 2,000 kilograms of water was dehumidified and collected at the cooling panel of air conditioner and recycled for irrigation. The rest of 42 kilograms of water was held in plants and substrate, and only 58 kilograms of water vapor was lost to the outside. So water use efficiency, or CUE, is 0.97. But in case of greenhouse, for example, this 2,000 kilograms is released to the outside. So water use efficiency is 0.02, meaning we can save water for growing plants by 97%. But this is a function of leaf area index and the number of exchanges per hour, or ventilation rate. Very high water use efficiency can be achieved only when CPPS is very airtight and plants are covering floor area or cultivation area. And the same thing can be said for CO2. But the problem is right, because amount of electricity for writing is enormous. So it's very important to improve light use efficiency or electric energy use efficiency. So method for improving electric energy efficiency is to use LED with a higher light energy conversion factor, and use a light source with optimal light quantity, photo period, and intensity. They place the light source close to leaves. They keep the direction of lighting to leaves only. And they use light reflectors with good design. They keep leaf area index or leaf area at around 3 by spacing. This is very important to improve EUE or LUE drastically. Keep the light source temperature at optimal level to get the maximum light energy output, and control the environment to maximize the net photosynthetic rate under a given lighting condition, and increase a portion of usable or edible part of plants by environmental control and cultivation system. The labeling the daily electricity consumption of lighting is important to reduce the electricity cost. Now I'd like to talk about method of online estimation of hourly net photosynthetic rate and the CO2 enrichment based on analysis of dynamic CO2 balance and of hourly carbon dioxide use efficiency and energy use efficiency. So this is a closed system, Cpps. We supply CO2 for promoting photosynthesis of plants. And we also supply electricity for lighting and air conditioning. But a very small amount of CO2 is released to the outside. But we can measure the CO2 supply rate very accurately. We can estimate this CO2 release rate using this equation. Then net photosynthetic rate can be estimated by this equation, supply rate minus release rate, and the change in CO2 amount in room air. Then we can estimate carbon or CO2 use efficiency by P divided by S. So we can estimate net photosynthetic rate online. Then we can do the same thing for water vapor or water use efficiency. And also, this equation, electric energy use efficiency, can be expressed by net photosynthetic rate divided by electric energy consumption. Normally, we measure and show the temperature, light level, or CO2 concentration, which are called state variables. But it is very important to measure or estimate rate variables, such as net photosynthetic rate, or water uptake rate, or transpiration rate. Then we can easily optimize the growth of plants at the lowest cost. And this is an example of our estimation, daily changes of net photosynthetic rate in PFLL. This was conducted by PFLL of Mirai company, a large one. Okay. Now this integrated environmental control system we can now we are developing this integrated environmental control system, considering value creation and cost. The cost consists of maintenance, traceability, and invested resource, and emission of environmental pollutants. Maximization of value created divided by cost of resources, safety, and environmental conservation can be achieved using this software. And I'll show you some ubiquitous in-town PFL very quickly. This is our showroom, and this is a small hospital in Tokyo, and this is office interior, rose garden in the building, and plant factory in the meeting room. And this is a small wall just behind, just in front of the restroom door. And this is for disabled or handicapped person working in the plant factory. Okay, this is a conclusion. Challenges in vertical farming. I picked up 5 challenges. One is detailed analysis of life cycle assessment, and developing simulators of vertical farming, and developing a distributed, intelligent, and integrative network system, and develop new industry incorporating environment, agriculture, food, IT, health industries, and optimization of space allotments in cities with respect to open field, semi-closed system, and closed system, living space, working space, or public space. Thank you very much.
Thank you, Dr. Kozai. In the interest of time, we'll have to save the questions, and you could ask Dr. Kozai in the panel. I'm sorry, we've got to get going here. Thank you.